When you think about human invention, it's almost always a story of imitation. We look at the eye and we build a camera. We see a bird take flight and we engineer an airplane. But the quest for artificial intelligence, well, that's something else entirely. It's on a completely different level, because the goal isn't to copy a physical part of the world, it's to copy the mind itself. Today, we're going to peel back the curtain. We're going to look past the chatbots and the cool image generators and step into the engine room, the mathematical heart of it all. We're going to explore how we take something as messy and abstract as a human thought and translate it into the cold, hard, logical language of calculus. So here's our game plan. We'll kick things off with the sheer ambition behind AI, and then dive into the 70-year civil war that defined its entire history. After that, we get our hands dirty. We'll dissect a digital neuron and explore the calculus that lets it learn. Then we'll zoom out to see the massive architectures of modern AI, and finally, we'll look at the horizon, at what's coming next. All right, let's start with that core ambition. Think about inventions like the wheel or the printing press. They solved concrete, physical problems, how to move things, how to store information. But AI is trying to solve the problem of understanding itself. It's an ambition that is just infinitely greater. And this right here is the monumental task. I mean, how do you do that? How do you replicate the actual process of thinking, of having an intuition, of genuine creativity? It means you have to somehow grab something that feels deeply subjective and human, like an idea, and pin it down with mathematics. You have to make it rigid, repeatable. You have to translate that messy, beautiful, biological process into a series of steps a computer can actually run. This is the fundamental concept you have to accept to understand any of this. Inside that machine, what we call intelligence is really just the final answer to a long series of incredibly complex equations. It's a deterministic result. There's this massive chasm between the warmth and weirdness of a human thought and the cold, precise calculation of a derivative. The entire history of artificial intelligence, it's all about building a bridge across that exact gap. Now, that journey wasn't some smooth, straight line of progress. Not at all. It was more like a fierce, 70-year-long intellectual civil war. A battle of ideas that shaped everything. Who got funding, which projects were pursued. It's even why we had these long, dark periods called AI winters, where progress just ground to a halt. And all of it, this entire conflict, was because the field was split into two camps, with two totally different answers to one basic question. How do you get knowledge into a machine? So here are the two sides. On your left, you have the symbolists. They were rationalists. They believed that you could build intelligence from the top down, with carefully programmed rules and logic. Their analogy was a perfect, all-knowing library. This is kind of like what the Nobel laureate Daniel Kahneman calls System 2 thinking. It's slow, logical, and deliberate. And on the right, you have the Connectionists. They were empiricists. They argued, no way, intelligence has to be learned from the bottom up, from data and experience, just like a child learns to walk. This is much closer to Kahneman's System 1, fast, intuitive, gut-feeling kind of thinking. But here's the thing. Both of these grand philosophies had a fatal flaw. For the symbolists, it was brittleness. Their perfect library just couldn't handle the messiness of the real world. You show it a weird-looking hairless dog that's coughing instead of barking, and its logic just shatters because it doesn't fit the pre-programmed rule. And for the Connectionists, their flaw was opacity. Their systems are total black boxes. A neural net might be incredibly good at spotting a tumor in a medical scan, but it can't tell you why. It can't explain the logical steps it took. It just knows, which is a huge problem. So after decades of fighting, the big realization of our time is that you need both. The war is finally over. The two sides are coming together, they're fusing into what we now call neuro-symbolic AI. The goal here is to build a hybrid system that gets the best of both worlds. You want the fast, intuitive System 1 perception of a neural network, combined with the slow, logical, and most importantly, verifiable System 2 reasoning of a symbolic system. You want a machine that can not only see the world, but can also think about it. Okay, so to really understand how this new combination works, we have to understand the pieces. We need to zoom way in. We're going to put the fundamental building block of all modern AI on the operating table. Let's dissect the artificial neuron, sometimes called a perceptron. This is the single atom from which all of this incredible complexity is built. Now, it's called a neuron, and yeah, it's inspired by the ones in our brains. But honestly, it's really just a simple little piece of math. A tiny numerical gatekeeper. Its entire job, everything it does, can be broken down into these 4 simple steps. It receives some data. It weighs that data based on importance. It adds a little baseline value, and then it makes the final decision. Do I fire a signal, or do I stay quiet? That's it. Let's make this concrete with a classic example. Let's say we're building an AI to predict the price of a house. The very first component is the inputs. We can just call them X. These are nothing more than the raw data points that describe the house. The square footage, number of bedrooms, the local crime rate, you name it. They're just the descriptive numbers that the neuron is going to look at. Okay, now we get to the absolute heart of it all. Seriously, if you only remember one thing, remember this. The next component is the weights, or W. A weight is just a multiplier that tells the neuron how important each input is. Think of it like a bunch of volume knobs on a giant mixing board. If square footage is a huge factor in a house's price, you turn that weight way up. If the color of the front door doesn't matter at all, you turn that weight way down, close to 0. The entire process of AI learning is nothing more than the machine figuring out how to adjust these knobs. That's the whole magic trick. The third piece of our puzzle is the bias, or B. This is just an extra number that gets added to the total, and it's totally independent of any of the inputs. Its job is to give the neuron a starting point, a baseline. In our house price example, think about an empty plot of land. It has 0 bedrooms and 0 square footage, but it still has value, right? The bias lets the model represent that baseline value. It's kind of like the neuron's built-in predisposition. And finally, we have the activation function. This part is the secret sauce, because without it, our neural network would only be able to learn simple, straight-line relationships. It could learn that more square footage always means a higher price. But the real world is way more complex than that, right? The activation function adds a twist, a curve. It allows the network to learn sophisticated patterns, like how the value of an extra bedroom might be huge in one neighborhood, but almost worthless in another. It's the final decision maker, and it's what lets the AI model the messy, non-linear world we actually live in. So, we've built our neuron. We understand the parts, the what. But when you first switch it on, it's just a pile of random parts. The weights are all wrong. It's totally useless. So now we get to the really cool part, the process of making it smart, the how. And this all relies on a beautiful feedback loop driven by 3 mathematical pillars, all powered by calculus. This right here is the 3-part engine that drives all of machine learning. It's a constant cycle. First, the AI makes a prediction. Then, the loss function acts like a scorecard, telling it exactly how wrong it was. Second, gradient descent acts as a compass. It uses that error score to calculate the single best direction to adjust its weights to be a little less wrong next time. And third, backpropagation is all about credit assignment. It's the process that figures out precisely how much blame each one of the millions of individual weights deserves for the total error. This loop repeats millions, maybe billions of times, and it's what transforms a network from a random mess into an intelligent system. To really get your head around gradient descent, the compass, there's a perfect analogy. Imagine you're a hiker standing on a vast mountain range, but you're blindfolded and in a thick fog. Your goal is to find the very bottom of the deepest valley. That valley represents the lowest possible air for the AI. Now, you can't see anything, but you can feel the slope of the ground right under your feet. That slope, the direction that points most steeply downhill, that is the gradient. It's the perfect compass. All you have to do is take one small step in that downhill direction. Feel the slope again, and repeat. Step by step by step, you will find the bottom. But, okay, gradient descent only tells you which way is downhill. It doesn't tell you which of the millions of weights to actually change. That is the job of backpropagation. And you can think of it as a highly structured mathematical blame game. The best analogy is a car factory. An inspector finds a defect in a car at the very end of the assembly line. To find the source of the problem, what does he do? He walks backward up the line, station by station, figuring out exactly how much blame each step in the process deserves for that final flaw. Backpropagation does the exact same thing, but with calculus efficiently figuring out how much every single weight contributed to the final mistake. Okay, so we have the atom, the neuron, and we have the engine that teaches it, the calculus of learning. Now it's time to zoom back out. Let's talk about how these individual atoms are assembled into massive structures. Because it turns out that how you wire all these neurons together, well, that matters a lot. This is where we get into the incredible architectures that define modern AI. For many years, these AI architectures were highly specialized. If you wanted an AI to see, you'd use something called a convolutional neural network, or a CNN. They were brilliant at finding patterns in pixels, basically acting as the eyes of AI. For language, you'd use a recurrent neural network, an RNN. These processed words one by one in sequence, which gave them a kind of short-term memory. The problem was, their memory was terrible. They'd forget the beginning of a long sentence by the time they got to the end. And solving that problem, the problem of attention, led to the massive breakthrough in 2017 that changed absolutely everything, the transformer. The key invention inside the transformer is a mechanism called self-attention. And this example shows you exactly why it's so powerful. Just look at these two sentences. They are almost identical. But in the first one, the animal didn't cross the street because it was too tired. The word "it" obviously refers to the animal. In the second sentence, the animal didn't cross the street because it was too wide. Just by changing one word, it now refers to the street. Before the transformer, that was an incredibly hard problem. But self-attention allows the model to look at every word in the sentence all at once, and to calculate these complex relationships between them, no matter how far apart they are. That is the secret sauce. And that brings us right up to the present moment, to the bleeding edge of AI development. And the reality is, we are now hitting a wall. A very real, very hard wall, the data wall. We are literally running out of high-quality human text on the internet to train these models. This means AI has to fundamentally change the way it learns. It has to evolve from being a passive reader of human knowledge to being an active doer in the world. From simulation to real experience. This is the next chapter. And the scale we're operating on now is it's hard to even comprehend. It's estimated that GPT-4 has around 1.8 trillion parameters. That's 1.8 trillion of those little weighted volume knobs we talked about, all being tuned at the same time. But it's important to keep that number in perspective. The human brain has roughly 600 trillion synapses. So even these massive models are still orders of magnitude less complex than what's in your head. And they are wildly less efficient. Your brain runs on the power of a dim light bulb. Training one of these big models consumes the energy of a small city. So I want to leave you with one final provocative thought to chew on. Artificial intelligence has now, for all practical purposes, read the entire human internet. To continue getting smarter, the only path forward is for it to start generating its own data to learn from. Data created by other AIs or from its own simulated experiences. So the question becomes, what happens when that becomes its main source of knowledge? What happens when AI starts learning primarily from other AI? Will the intelligence that emerges still reflect human reality, or will it begin to drift away into its own purely self-referential world, creating a cognitive landscape completely alien to the human experience it was originally designed to imitate?